Welcome. In this video I'll go through pressure-driven modes, and we've seen a little bit before in a previous introduction, but here I'll concentrate on the sausage instability and look at how it behaves in MHD picture and in a single particle picture. And often there are at least these two different ways of looking at plasma phenomena, either as a fluid or as particles, and the end result is the same, but each has a different interpretation and different way of thinking about the problem, so it's useful to see things in different ways. Today we're going to look at pressure-driven modes, which are things driven by, in the energy equation there's a term in the delta W, the plasma equation. So we have a term which is like the integral over the volume of here we have a -2, we have a psi, which is the perturbation perpendicular to the equilibrium magnetic field. We have a pressure gradient, the equilibrium pressure gradient, and we have a curvature term. So it's again perpendicular, and this is the kappa. And there are other terms in here, but this is the one we're looking at the moment. So this can be positive, in which case it's stabilizing, or it can be negative, in which case it's destabilizing. So it's destabilizing if grad p here and kappa in the same direction. So if we have grad p naught dot kappa is greater than 0. And this happens when you have a magnetic field which is curved in towards the direction of the highest pressure. So this is B field here, so we have kappa going inwards and into the middle of the curve, and then you have the pressure gradient, which say is going this way. So if this was grad P this way, so we have high pressure here and low pressure here. Then this would be unstable. And the configuration where this occurs is the Z pinch. And so here you have a cylinder, a cylindrical plasma like this. And you have a current running down the middle. So let's draw that as here. This is the current. IP is the plasma current. And it's driven by some external power supply. And this is producing a magnetic field around in this direction here. So a magnetic field going around the plasma, and this is providing an inwards force. So the current combined with the magnetic field, here called B theta, is the poloidal field around here, is producing an inwards force, so that the grad P is inwards, so that high pressure in the middle and low pressure on the outside, and of course curvature is here is also inwards. So this is curving, so curvature is also inwards towards the center of the machine, or center of the plasma. And so here we have kappa dot grad P is greater than 0. So this is unstable to pressure-driven modes. One of them is so-called sausage instability, where essentially parts of the plasma expand, parts contract, and so we end up with, so I'll draw that again better. So we end up with parts of the plasma expanding, parts contracting, and you can end up with a kind of like a chain of sausages. The parts are constricted. So here this part is also in like this. So parts of the plasma have been constricted, reduced in size, and parts have expanded. And this particular instability has an m equals 0, so it's constant around this direction. So the whole thing is expanding here and contracting. And so the radius of the plasma, we call this R. This radius is expanding here and it's getting smaller. And now there are a few different ways of thinking about this. The first is the MHD kind of picture. So what we have here is we have a current through the middle, and so you can work out the poloidal field from the integral of B dot dl is just mu naught times IP. And if this is just a circular plasma, then this is just poloidal field times 2 pi r. So this whole thing is B theta times 2 pi r is equal to mu naught IP. And so therefore the poloidal field at the edge of the plasma is just mu naught IP divided by 2 pi r. And so as the plasma expands, the magnetic field gets weaker, and as the plasma contracts, so the R gets smaller, then the field gets stronger. And so what we end up with is strong magnetic fields around this region, and weak magnetic fields around the large regions here. And so these strong magnetic fields then provide a higher inwards force, because we can write down the force balance equation for a Z pinch. This was derived quite a few lectures ago. So in equilibrium, at least, we have the d by dr of the plasma pressure plus the magnetic pressure, which is b theta squared over 2 mu naught, plus the magnetic tension term is b theta squared over r mu naught, and this is equal to 0 in equilibrium. And so now as the plasma gets smaller, these terms get larger, because as r is decreased, b theta increases, and the magnetic tension and magnetic pressure both increase, and this leads to further constricting of the plasma. And the opposite, when the plasma gets bigger, this field gets weaker, and so the plasma pressure then dominates and pushes the plasma out. And so there's a runaway process where expanding plasmas expand even further, and contracting plasma keeps on contracting. And so the whole plasma breaks up into these kind of chunks with this wavelength along the field line. So that's kind of MHD picture in terms of an increasing or decreasing magnetic field as the radius is changed, and then the radial force balance. The other way of thinking about it is in terms of particle orbits. So the particle picture of these instabilities. So if we draw again magnetic fields with a curvature like this, so this is the B field, this is the curvature. If you have a particle orbiting around a magnetic field which is curved, there's essentially a centrifugal force on the particle, and this leads to a drift. And there's a drift in which is either into or out of the page depending on the charge. So for ions, for example, this is the drift is into the page. It's called V kappa is the drift. And we can write this down as the drift. So drift V kappa is, I have minus V parallel squared, and omega here is the cyclotron frequency. So this is the parallel speed of the particle, so the speed of the particle moving along here, and then this is times kappa cross B. Well, B is the unit vector, kappa is the curvature, and omega is the cyclotron frequency, which is just QB over M, where Q is the charge. And this is obviously positive for ions, and then negative for electrons. And so the sign of this changes. So ions drift into the page, electrons drift out of the page. And so if we look at the plasma now from the side, if you have an initially straight plasma column with the magnetic field going kind of around this way. So kappa is inwards, B is down here, going down at the front. And so you have that the ions, for example, are drifting this way, and electrons drift the other way. So electrons drift that way. And so if we have a small perturbation, so if this plasma moves up, then down, then up, for example, so there's some small perturbation to the shape of the plasma. So what happens now is that all the ions continue to drift to the right, and so we end up with essentially the ions drifting like this, and the electrons continue drifting to the left, and so the electrons drift like this. And so what happens is, in this region where we have say more ions than electrons, here we have a positive charge. So we have a positive charge region. So in this region over here we have more electrons than we have ions, and so in this region here we have a negative charge. And so what you end up with is an electric field which is a different colour for the electric field. So the electric field is going from positive to negative, so we have an electric field that way. and of course be the same over here, so we have electric fields like that. So the electric field this way, magnetic field that way, will produce an E cross B drift, which is inwards. So we have E cross B drift. And on the peaks of here, you end up with the same thing happening. So here the electrons have drifted this way, and the ions have drifted that way, and so you end up with here with the net positive charge like this, and on the other side we end up with a net negative charge. So on this side here we'll have a net negative charge here where the electrons built up, and so on this side we have the electric field going left to right. So now we have electric field going this way. And so the E cross B drift is now vertical. So here at this point, E cross B drift is this way. And you can see what's happened is that because of the drifts of the ions and electrons in opposite directions, you have an E cross B electric field set up, and that E cross B drift enhances the initial perturbation. So if you have any small perturbation, it will create electric fields which enhance it. And this is the same instability as the MHD picture. It's just a different way of looking at it in terms of particle drifts rather than forces or currents in the fluid. So there are always these two different ways of looking at the same instabilities, but they give the same answers in the end. So you can use whichever one is most convenient.